Hello, everybody. So now I'm going to talk about intrinsic flat convergence and some history of our main results. So this slide is how to prove Gromov-Hausdorff or intrinsic flat convergence to M0. If you are used to Gromov-Hausdorff convergence, this will ring a bell to you. So if we have a sequence Mj, and a manifold M0, what we have to do is isometrically embed Mj and M0 into a bigger space, Zj. Zj is not necessarily a manifold, it just has to be a metric space. And once that we embed M0 and Mj, inside Cj, we can calculate the Hausdorff distance or the flat distance. So in this picture, I have an M and I have an M1, and I chose as Z1 this type of cylinder. So it's U1 times minus H1 comma H2. I should have added the splines, by the way. So in these figures, Z1, we can calculate the Hausdorff distance or the flat distance. And because the Hausdorff distance is an upper estimate for the Gromov-Hausdorff distance, or the flat distance is an upper estimate for the intrinsic flat distance. When we have isometric embeddings, if we manage to prove that in the limit this goes to 0, so these distances go to 0, then we will have that the Gromov-Hausdorff or the intrinsic flat distance also goes to 0. So then we were able to prove that Mj converges to M0. Okay, so now let me give you more details about intrinsic flat convergence. In this slide, I'm going to tell you what is this distance. So this distance is defined for triples of this form. So you will have a metric space, and then you will have a T1. This T1 is an integral current, m-dimensional integral current. And what I'm going to tell you is that this current is a linear functional. I'm not going to explain more. For more details about intrinsic flat distance, you can see the videos by Cristina Sormani, or also the videos by Brian Allen, in which he explains very well how the intuition on this distance. But so once that we have these triples, if we want to calculate the intrinsic flat distance between them, what we have to do is isometrically embed x1 and x2 into a bigger complete metric space Z. And once that we embedded x1 and x2, we can also take the push forward of T1, of this linear functional T1, and we can also take the push forward of the functional T2, and there we calculate their flat distance. So some of the comments is that this distance is not really a distance you have to caution out, because two triples like this can have distance equal to 0, intrinsic flat distance equal to 0, if there exists an isometry between the metric spaces that takes one linear functional to the other one. And the second remark is that since we are going to be studying Riemannian manifolds, for a Riemannian manifold, we can assign a triple that is going to be an integral current space. And what we have to do is write m, then the distance with respect to the Riemannian tensor. And then we have this linear functional m double brackets. And that means that we are integrating forms, omega, that are defined on m, top forms. And we integrate these top forms over m. Okay, so let me continue. So the definition that I gave you before for intrinsic flat distance uses currents that were defined by Ambrosio and Kirchheim. These currents are a generalization of the currents that were used by Federer and Fleming in Euclidean space to prove the Plateau problem. And the flat distance is defined as follows. So we are in a big space set, and in this big space, we have two currents, T1 and T2. They should have the same dimension. And what we want to do is we want to satisfy this equation. So we want linear functional T2 minus linear functional T1 to be equal to U plus boundary of B. So this U and this B are also linear functionals. And once that we have a linear functionals U and B that satisfy this equation, we want to take the mass of U and the mass of V. So for Riemannian manifolds, the mass is going to be the volume. So we take the m dimensional volume, and here we will take an m plus 1 dimensional volume. And we take the infimum over all possible sets U and B. So this is the picture that explains better what is going on. So here, imagine that set equals R2. And then we have linear functional T1, which is going to be integrating over this red line with this orientation. And T2 will be integration over the blue line or blue curve with this orientation. And then we are going to choose U as the sides of this figure. So here we have in green, this is U, and this part is also U. And as V, so V is going to have one dimension more, so it's 2 dimensions, and it will correspond to integrating 2 forms over this yellow region. So with the appropriate orientations, we will be able to satisfy this equation, and then we can calculate the mass of U, which now is the length of the green parts, plus the area of the yellow part. And that is going to give us an upper estimate of the flat distance between T1 and T2. So now that we know the distance, what is this flat distance, we are able to look at more examples. These examples are going to be relevant for the explanation of the proofs of the main theorems. So 1 and 2 is just to remind you that we have to isometrically embed M0 and our manifold M1 or MJ into a bigger space. And there we calculate the flat distance, and this is an upper estimate of the intrinsic flat distance. So let's look at the first example. In this first example, I have a manifold M, which is compact and oriented, and I will choose two manifolds, so M0 and MH, to be equal to M, and I want to calculate their intrinsic flat distance. So we isometrically embed M0 and MH in a bigger space, and my bigger space is going to be this set. Set is M times an interval. So when I do this isometric embedding, I can take C, I can take C and then calculate its boundary. So when I calculate the boundary of C, what I'm going to get, if you look at this picture, I'm going to get the bottom part, so that's going to be M0, and I'm going to get the top part, MH, and I'm going to get the boundary that is vertical, the boundary of the cylinder that is just vertical. So then I'm satisfying the equation that I told you that we should satisfy in order to calculate flat distance. So then what we get is that the intrinsic flat distance between M0 and MH is going to be less or equal than the flat distance of the push forwards. And here I have the mass of set and the mass of the other part. And this mass can be easily calculated. So it's going to be H volume of M plus H volume of the boundary of M. Okay, so next example. Here again, I have M that is compact and oriented, and I'm going to have N0 to be smaller. So it's going to be 1/2 of M, like in this picture. And NH is just going to be M. So then we have to construct a set in which we isometrically embed these two manifolds. So set is going to be as depicted. So it looks like a truncated cone. So once that we have this truncated cone, we can again take the boundary of this cone, and the boundary of this cone, well, it's going to be the top part minus the bottom part, and then the other part of the boundary. So we will be satisfying the equation that we want to calculate flat distance in this truncated cone. And so we have that intrinsic flat distance between M0 and NH is less or equal than the flat distance in the truncated cone of the push forwards of N0 and NH. And here we can calculate, well, this is going to be by definition, if we choose these currents, this yellow current and this green current is going to be then by definition the volume of Z and the volume of this part. And this one, because I have one Lipschitz map between the cylinder and the truncated cone, is going to be less or equal than H, the volume of M, plus H, the volume of the boundary of M. So it's the same as what we had in the previous example. Okay, so these are the examples that I wanted to show you. Now let me tell you about the history of our main results. So Allen-Sormani proved in 2019 the following theorem, which is very similar to our main theorems. There they have a fixed manifold M, which is closed, so no boundary. And the conditions that they required is that Gj has two-sided bounds. So G0 is less or equal than Gj, and Gj is less or equal than Kj0. So we didn't have this condition in our main theorems. This is a condition that is very powerful, so they get diameter bounds of Mj. And also, because of this condition, they get zero convergence of the distance functions and Gromov-Hausdorff convergence and intrinsic flat convergence. And of course, the volume is preserved because they have it as a hypothesis. The remarks about this theorem are as follows. The volume convergence can be replaced by the LP convergence of Gj minus G0 to 0 for some P. So here P doesn't need to be M over 2 as in the previous theorems. And let me tell you a little bit how to prove this theorem. So this theorem, because we have these double-sided bounds on the tensors Gj, we will be able to use Arcellas-Colli to find a distance, d infinity, to which dj, or a subsequence, so djk, is going to converge to d infinity. So once that we have this distance d infinity, well, we have this space, this metric space M infinity, which is M to the infinity. So the claim is that it converges, our sequence or our subsequence converges in a Gromov-Hausdorff sense and intrinsic flat sense to this metric space. And to do so, well, it follows almost right away by the theory of intrinsic flat distance, but to do so, one can also do the following. So we can construct a space Zk in which we can isometrically embed M infinity and Mjk. And this space is very similar to what I showed you in the previous part of my talk. So it's going to be M times an interval. Here we have to give a metric to this set. And this metric is not the product metric, it's more complicated, but we are able to isometrically embed M infinity and Mjk. So once that we have this metric space, set K, we can calculate the Hausdorff distance, and this this flat distance, or well, just Hausdorff or flat distance, and this is going to go to 0. Okay, and now the remaining part is that we want to conclude that this space M infinity given by M d infinity is equal to to the manifold that we started, M0. And for that, they use a result that tells you that there is almost everywhere convergence of distance functions, so dj to d0. So let's look at the next slide. So in this next slide, what we have is the following. Again, we have a closed Riemannian manifold, M, and we have this inequality at the level of the Riemannian tensors, and we have the volume convergence. So under these conditions, Sormani and Allen are able to prove that up to a subsequence, the djk converges to d0 pointwisely almost everywhere. So this theorem, notice that this theorem is used in the previous theorem to conclude that d infinity equals d0, but this is not used to construct set k or d set k. This is going to be very different in the proof of our main theorems. We will use this theorem by Allen-Sormani to construct spaces set jk in which to embed our manifolds mj and m0. And this theorem also holds if M has boundary, but we require totally convex interior with respect to the Riemannian tensor G0. So this is some of the bibliography that I talk about during this part of my talk.